Welcome back, everyone, to another explainer. Today, we're diving deep into the architecture of OmniRoute to see exactly how it unifies what is, honestly, a completely chaotic AI landscape right now. We're looking at a system that takes hundreds of totally distinct AI services and basically forces them to play nicely together behind a single door.
So think about the core engineering problem here for a second. The real challenge isn't just supporting hundreds of AI providers on a base technical level. The real puzzle is figuring out how to make completely different, utterly incompatible systems act as a single local first endpoint. We're talking about different request formats, wildly different authentication methods, unique model identifiers, totally separate streaming protocols, the whole shebang. Yet somehow, this tool attempts to corral all of them so they appear behind one simple, OpenAI-compatible endpoint. To see how they actually pull this off, we're going to track a single API request through 6 crucial stages. We'll look at the API compatibility problem, the translation abstraction, smart routing and resilience, the context compression pipeline, operational state and data, and finally, the implementation stack. We're literally tracing it from the exact moment it leaves your IDE to the second it hits the provider. Okay, kicking things off with stage 1, the API compatibility problem. And let's be real, the absolute chaos of the current ecosystem.
Despite all these distinct interfaces and rules, whether you're dealing with Anthropic's message format or Gemini's totally unique structure, OmniRoute forces them all behind one simple localhost port. Imagine your coding agent or your CLI sending what looks like a completely standard API request to this local endpoint. But behind the scenes, OmniRoute isn't just lazily forwarding HTTP traffic like a standard proxy, it's acting as a highly sophisticated inference gateway.
Right, which brings us to stage 2, the translation abstraction. Let's look at how the system actually goes about normalizing these wild requests. Picture your request packet leaving your IDE and hitting this translation layer. First, the request gets normalized. OmniRoute detects the expected source and destination formats, and it actively converts the request before it ever dispatches it. It might swap around message roles, translate tool definitions, handle multimodal content, you name it. It transforms your request into whatever native format the target actually wants. And then, when the provider finally responds, that data just travels in reverse. The streaming events are translated right back into the format your client originally expected. The ultimate routing decision is hidden so perfectly behind this boundary that your client application has literally no idea which provider actually handled the request. So the request is translated. What's next? Stage 3, smart routing and resilience, where the system figures out exactly where to send it. This is a huge shift in thinking. In this system, a model name is no longer just a model. It's an abstraction over dynamic routing behaviors. OmniRoute doesn't just route at the provider level because, think about it, 2 API keys for the exact same provider might have completely different quotas. So they group targets into these structures called combos. A combo might be a simple fallback chain, or it could be this incredibly complex execution policy for load balancing, cost-aware selection, or even these really cool fusion pipelines where a request gets sent to multiple models simultaneously, and then another model synthesizes the results. It's wild. So instead of hard-coding one fixed model, the router assigns the request to the best possible target dynamically, using real-time operational signals. It's constantly checking provider health, looking at your remaining quota, evaluating latency, reviewing recent success rates. The model you selected in your IDE could resolve to an entirely different provider and connection on every single request, just based on what makes the absolute most sense in that exact second. But wait, what happens when things break? Because they definitely will. This is where the router gets super smart and stateful. It uses distinct layers of resilience to avoid retry storms while keeping your requests flowing. Say a provider starts throwing 500 errors. A provider circuit breaker trips, so you don't waste time banging on a broken door. But if you just hit a rate limit on one specific API key, a connection cooldown isolates only that account, leaving your other accounts for that provider totally available. By identifying failures at the exact scope they happen, the system saves healthy capacity and ensures your development flow doesn't just crash from one isolated hiccup. All right, before that payload even reaches the provider, we hit stage 4, the context compression pipeline.
You see, OmniRoute doesn't just blindly throw massive context windows upstream. It runs them through a pipeline of independently configurable compression engines. One engine deduplicates conversation turns. Another one, which is cleverly called RTK, filters out all those massive repetitive shell outputs and diffs. There's even a semantic tool called Caveman that prunes lower value context. The project claims this 10-stage stacked configuration can save anywhere from 15 to 95% of eligible tokens, especially in heavy tool use sessions. Now, keep in mind, this is a project-reported result, not a guaranteed metric for literally every workload, but the concept itself is a massive money and context saver.
What's really crucial here, though, is that this is a carefully controlled pipeline with built-in escape hatches. It respects preservation boundaries. It knows not to compress or truncate your code blocks, your URLs, or your JSON schemas. It isn't just lazily asking a cheaper model to summarize your text. It's surgically removing the bloat while completely protecting the exact syntax your coding agent needs to actually function.
Moving right along to stage 5, operational state and data. Where does all this memory, configuration, and routing state actually live?
OmniRoute is basically split into two halves, both powered by a local SQLite database. On one side, you have the data plane, which is just busy carrying your actual inference requests. On the other side is the control plane, deciding how those requests should be handled. And because it exposes machine-to-machine protocols like MCP and A2A, AI agents can actually inspect and operate the gateway itself. Think about that for a second. The routing policy can be modified on the fly by the exact same AI agents whose requests are being routed. The AI can query the system's health, manage its own memory, or alter configs dynamically.
We really need to clarify the local first boundary here because it's an important distinction. Your operational state, your credentials, your SQLite database, and all that brilliant routing logic we just talked about, that stays strictly on your local device. There is no mandatory cloud service sitting in the middle harvesting your telemetry. But your actual prompts still travel to whichever upstream provider you dynamically selected. So the gateway architecture is entirely local, but the heavy LLM compute is still happening on OpenAI or Anthropic servers.
Finally, let's wrap up this journey with stage 6, the implementation stack, and see what's powering this under the hood.
The sheer scope of this open source project is honestly fascinating. Under the hood, it combines a Node.js, TypeScript, and Next.js server with a React dashboard. It uses server-sent events for streaming and a WebSocket bridge for compatible clients. I mean, this single stack is serving as an API adapter, a dynamic policy engine, a stateful resilience system, a context compressor, and a desktop dashboard. It makes it incredibly powerful, but as developers, we also know that packing that much responsibility into one repository definitely makes it complex to maintain over time.
But if we zoom all the way out, looking at the big picture, the entire architecture of this gateway basically boils down to 3 essential verbs. Normalize, forcing incompatible providers behind one standard interface. Decide, intelligently selecting the best provider, model, and connection based on real-time data. And recover, gracefully handling failures at the exact scope they happen so your client application doesn't just crash.
And that brings us to the ultimate takeaway. Thanks for hanging out for this explainer. Looking at how OmniRoute acts as this stateful policy engine rather than just a dumb proxy, it really makes you wonder, how are these intelligent local-first gateways going to fundamentally change how we build software going forward? When your infrastructure is smart enough to self-heal and route around broken APIs in milliseconds, what kind of incredibly complex, multi-agent systems are we going to be able to build next? It is a fascinating space to watch for sure. Keep exploring, and I'll catch you next time.